Swayam Prabha. Digital India. Educated India.
Good afternoon, everyone, and today we will continue with module 4, which is principles of texture measurements by X-ray diffraction. This is lecture number 27, and in this lecture we will learn the limitations and errors in X-ray texture measurements and corrections and their corrections. So, the concepts that will be covered in this lecture are background error, defocusing error, absorption error, the influence of counting statistics, and normalization to multiples of random orientation distribution MRD, as we call it in abbreviated form. So, you see that the first thing that happens when we calculate pole figure is that along with the peak there comes the background. So, here is one case, the first case, case A, where the background BG A1 and BG A2 have a little difference. So, BG A1 is little larger than BG A2. On the other hand, in the case B, BG, that is background B, is constant in both the directions. So, you see, for different measurements of theta or different measurements of alpha, the background may be different in either sides or same in both the sides, right. So, you see how the background is created. The background occurs because of the presence of incoherent scattering and fluorescence in the sample. There could be interaction with the air, collimator, beam stop and electronic noise, which can create background. On the other hand, you see short wave components of continuous spectrum also excites fluorescence, which creates background. Background is basically created when k beta absorption filter is used, because in that direction the background along with the k beta is removed, but on the other direction on the higher of lambda there is still a background. Now, you see energy dispersive detector is used to reduce background intensities at different wavelengths, right. But you see the background is mostly reduced or can be reduced technically, instrumentally, through using a narrow receiving slit. But you will see that by using a narrow receiving slit we will increase the defocusing error. Defocusing error we will teach in the next slides, coming slides. So, you see what we basically do, the background that we have here is basically removed by subtracting the background or the average of the background from the measured intensity of the peaks for the whole alpha beta. So, you see the intensity of the alpha and beta, the corrected intensity is equal to intensity measured minus BGA or BGB, whatever it is. So, now BGA can be obtained, you will see, by measuring the complete pole figure away from the Bragg's diffraction peak. So, we have to measure the complete pole figure, the alpha beta scan at a theta which is away from theta which fulfills the Bragg's law. And then you see what we do, we calculate the background for increasing alpha and then we just have to integrate it over the beta, because the background error does not change with the change in the beta from 0 to 360, only it varies when the alpha is increased or the theta is increased. Now, the BGA 1 and BGA 2 are non-Bragg's theta on both side of theta A, which is the Bragg's condition, right. Now, considering while we calculate this background correction or the background error, we have to consider the peak broadening which occurs when the alpha is increasing. So, we should remember that the intensity peaks at Bragg's angle are very sharp when the alpha is less, and when the alpha increases the intensity peaks broaden, right. Total intensity of that peak remains same, but the intensity peak reduces and it gets broadened. So, secondly, while we are calculating this background, we have to be very sure that there must not be interference between the neighboring peaks. So, you see that as alpha increases, the background intensity basically decreases, right. Background intensity basically is most of the time independent of the theta, and therefore, the background is basically measured with increasing alpha for any particular theta and then is integrated over the beta, right. And that is how we calculate the background, and then we subtract the background from the measured intensity to get the correct intensity for alpha and beta for obtaining intensity peaks for a pole figure. The second most important error that occurs during the calculation of the pole figure, calculation of the alpha beta scan, is defocusing error. You see the setup schematically looks something like this, right. This is a schematic of the setup. We have the divergent incident beam. So, here is the X-ray beam which is divergent, is falling on the sample, and here is the convergent beam which is diffracted from the sample and is going to the detector. So, the detector is at some position where the convergent beam is focused, right. So, theta is the Bragg's angle. As I said, alpha is the rotation that occurs along the TD. So, alpha is equal to 0 and then it increases to 10, 5, 15 and 20 and 45, and then it goes to 70 in the minus, because it is in the using the right hand thumb rule. It is not in the right hand thumb rule, it is in the left hand thumb rule. So, it is minus. Now, you see that when the alpha is 0, that means there is no tilt, and the theta is at 90 degrees. That means, when the source of the X-ray is kept here and it is falling over here. So, the theta, which is the angle between this incident beam and the TD, is 90 degrees. Then you see that as per geometry of the electromagnetic radiation incidenting on the surface at 90 degrees, the incidenting beam will have exactly circular what you call it, shape falling over the sample. Now, as this is the point where the focusing is 100% true, because alpha is equal to 0 and there is the theta is 90 degrees. But you see that when we increase the theta, now see in this case you see that when theta is equal to 90 degree, the incident beam and the detector should be at the same position to get any kind of intensity or diffraction, which is not possible. Definitely theta has to be less than 90 degree to get a diffraction. So, as theta is decreasing and it reaches say for example 45 degrees. So, once theta is decreasing from 90 degrees to 85 and 80 and it goes to 45 degrees, slowly and slowly defocusing starts. So, the beam starts to get elongated horizontally, you see. So, as this beam, the incident diffracted incident beam X-ray beam is the theta is decreased from 90 degree and it goes like this and it is falling like this and it goes like this to become 45 degree. The the beam becomes elongated while it falls on the surface. When it becomes higher at theta equal to 10 degree, it becomes too much elongated, because you see when the beam is falling from this direction, the beam will be spreading out over the sample and it looks something like this. Now, what happens when alpha is increased? So, when alpha is increased, so there is a rotation of 45 degree in this direction. So, you see when it is rotated by this direction, means by the left hand thumb rule, okay, you see what will happen, that the beam when theta is at 90 degree, the beam which was initially circular, it will become elongated vertically, and when the alpha will increase to 70 degree, it will further elongate, right. When both theta and alpha is increasing, you will see the elongation occurring at a diagonally, and it keeps on increasing, and once you see that as the sample is rotated by alpha, this is the sample at alpha equal to 0, when the sample is in such a way that it is in the most focused condition as the incident beam is diffracting and it is falling on the surface, and then it is getting focused here fully. As the alpha is increased from 0 to 10, minus 10 and then 30 and 45 whatever, then what happens, that apart from this line of the sample, the plane, this plane on that side and the plane this side of the sample becomes both defocused, because the sample is now rotated by a certain angle by alpha. So, you see the sample is face out of the focusing plane. That means that except this line which is getting focused here on the detector, neither the plane which is on that side of the line and this and towards my side of the line is getting focused properly at the detector. So, two things is happening. First, the focusing is gone. Second, the beam is highly spread out. So, it is highly elongated and distorted. So, you see two things that has to be considered. First is the penetration depth. The penetration depth will change. Second, not all diffracted beam, now the diffracted beam is highly spread. So, not all diffracted beam will now enter into the detector, and neither it will enter in fully focused form, right. So, you see as the beam has a large spread while after the diffraction. So, all the recorded intensity may decrease, because you see the receiving slit may have a constant diameter, right. So, it takes only a part of the incident beam the diffracted beam, because now the diffracted beam's radius is much larger. So, the recorded intensity will reduce. Secondly, you see when theta becomes very small, is less than 10 degree, it cannot be measured, because you see the spread here has become so large, when as alpha will start to increase, the spread will be larger and larger. So, now we comes to the penetration depth. Now, you see that in case of reflection geometry, the problem of absorption is not that much. You see that as the spread increases, the absorption increases, but you see it is balanced by the increase in the irradiation volume. So, penetration depth will have no issue in case of the reflection geometry, but it will become an issue when it is a case of transmission geometry, that is for example, in synchrotron radiation or in neutron diffraction. So, the beam becomes totally defocused when the tilt angle alpha becomes greater than 70 degree. The most important thing to remember is that at large tilt angle, all diffracted beam does not enter the detector, because the receiving slit has a certain dimension, right, and therefore, it is only due to the geometric region this defocusing error basically occurs. So, now we will look into defocusing error correction. You see that when we do an alpha beta scan to obtain a pole figure for a certain theta, say for example, for either an HKL 200 or for an HKL 110. Say for example, this is for a certain body centered cubic material which diffracts at a 2 theta of 64.5 degree for 200 HKL and 42 degree for 110, and say that we assume that in both the case the intensity or the texture of 200 and 110 is almost the same. Now, let us look into this figure. You see that in order to obtain a better intensity, a optimum result from the diffraction, the X-ray beam, which is basically divergent, we use a large divergent slit, so that larger and larger beams enter and falls on the specimen. On the other hand, in order to reduce the background error, we use a very narrow receiving slit. But as I said in the last slide, that when the theta is high and the alpha is low, the peak is sharp, right. You can see it here, the peak is sharp, and you can see that for a higher theta, the peak is sharp for a particular alpha, say alpha equal to 0, and for a lower theta, the peak is basically it has a less peak considering the same intensity, but you see the total area of this peak for both the case will be same if the intensity of the texture is same for the HKL plane 200 and 110, and this is a hypothetical situation that we are talking about. Now, when the alpha is basically increased or the theta is basically reduced, say for example, in this case let us keep the theta same and let us increase the alpha. What happens that, as for example, in this case when the alpha is 0 for HKL equal to 200 and for 2 theta equal to 64.5, the intensity peak is very high, the integral breadth is very low. At alpha equal to 45, the intensity peak reduces a lot and the integral breadth increases. Now, the area under this curve, both this curve remains the same because it is for the same peak, and when alpha increases to 70 degree, the integral breadth increases to a much higher extent, whereas the peak decreases much largely. Now, what happens that because we use a narrow receiving slit, as the integral breadth of the intensity peak increases with the increase in the alpha, the narrow receiving slit restricts the entry of the total peak in order to remove the background, and therefore, the recorded intensity is from a very small area, and thus the recorded intensity basically decreases. The same thing happens for the different theta for another HKL plane. So, you see that in order to carry out defocusing correction, what we need to do is that we need to use a wider receiving slit. A wider receiving slit will help us to take the whole intensity while the peak has been broadened. A smaller divergent slit will help us to obtain a smaller divergent incident beam, and thereby the receiving slit or the detector will the intensity will not reduce that much when the narrow receiving slit is used in the diffracted beam, and therefore, almost all the intensity will enter the detector. But you see, a wider receiving slit and a smaller divergent beam both will increase the background. So, one can think like we can increase the value of lambda, the wavelength. So, we can use a different instead of a particular characteristic wavelength, one can use a wavelength which is of higher lambda, right, X-ray beam of an higher lambda. So, that one can increase the Bragg's angle theta, and thereby one can get a reduced defocusing error. But you see, it will also increase the absorption, mass absorption coefficient. Of course, it will not affect in case of the reflection geometry, and it will affect mostly in case of transmission geometry. So, up to alpha equal to 45 degrees, there is in most cases there is no correction needed. From alpha equal to 45 to 70 degrees, one can do a correction, and then one can obtain the corrected curve or the corrected intensity, removing both defocusing and the background. For alpha greater than 70 degrees, the defocusing is so much that further correction is not possible. Therefore, while we do the pole figure measurement, alpha beta measurement, the alpha is measured, the pole figure is measured up to alpha equal to 70 degree and not beyond that. So, if we look closely, as alpha increases, the diffraction peak basically diffraction peak intensity basically decreases, and this accompanies with the broadening. So, as I said in the last slide, that a small and a constant area of a receiving slit, the detector will only observe a small and a constant sample area, and because of the peak broadening, the intensity that will enter the detector because of this narrow slit will keep on decreasing, and therefore, what we will have a decrease in the intensity, overall intensity. So, if we look into the intensity with respect to the change in alpha, and it is normalized by the intensity at alpha equal to 0, then we find that for different angles, means the different Bragg's angles, 2 theta angles, the change in the intensity curve is not that different. Yes, there is a slight difference. So, what it is done, a correction function is u alpha, say u alpha is a correction function, is applied to correct this defocusing error. So, you see the intensity corrected is equal to the intensity measured minus the background correction divided by u alpha, which is the defocusing correction, right. So, the defocusing correction is needed to increase the intensity as alpha is increasing in the pole figure, right. U alpha is obtained by the measurement of, means it is best when you calculate the u alpha from the random sample for an alpha beta measurement, right. So, pole figure of a randomly textured sample are measured at Bragg's angle theta as alpha is increasing, and it can be integrated over the whole beta because it does not change for the beta. So, we do not have to measure from beta equal to 0 to 360 degrees, and then it has to be normalized with respect to u alpha for alpha equal to 0 degrees, and it has to be made equal to 1. So, you see that for measuring the pole figure, what we found out from the discussion, we found out that there has to be 3 pole figures of lowest Miller indices that is usually measured, that has to be measured. And because you see one pole figure will not give the total information. The first reason is that a single pole figure only gives the plane normal, and it does not give the direction of the plane, that important direction of the plane. So, the plane normal we only have. So, the plane can be rotated, right, on the plane, the particular direction at which a certain important reference sample reference direction is there is not notified for by a single pole figure. It only gives the normal to the plane. The second thing is the pole figure could only measure up to alpha equal to 70 degree, because it will get fully defocused after 70 degree. So, you see we have to measure multiple pole figures all from 0 to 70 degrees, and then we have to take that data, all this at least these 3 pole figure data from alpha equal to 0 to 70 degree, and only the data which contains the normal pole of the particular plane, HKL plane, or 3 different HKL planes that are measured, right. And from that the back calculation is done, and the total pole figure or the calculated pole figure is obtained, which is from alpha equal to 0 to 90 degrees for all the cases. And from these, the inverse pole figures, the important Miller indices, the orientation matrix, the Euler angles or the Euler space or the orientation distribution functions could be measured or obtained, okay, actually calculated. So, as I said that absorption is not very important factor in case of reflection geometry in X-ray diffraction for measuring the pole figure, but in case of transmission geometry absorption is a very important factor. Say, because you see when in the transmission geometry we use thin samples, and it is the electromagnetic radiation, X-ray radiation passes through the sample and gives the diffraction in the transmission mode definitely. So, you see if the intensity of the applied radiation, intensity of a sample of a certain thickness T is I T, and the intensity that can obtain for an infinite thick sample is this, then this is given by 1 minus exponential to the power 2 mu t. Mu is the linear absorption coefficient, t is the thickness, sin theta is the Bragg's peak, and for a particular alpha cos alpha, right. So, this is basically the absorption intensity that we need to know. Now, another important thing is the counting statistics. You see that the larger the counting or the larger the statistics for the certain peak, then the standard deviation of the peak basically reduces. So, if you see that n is the number of counts, derived per unit time at a given sample position, and this is subjected to a statistical scatter. Now, if NP is the number of counts at the certain Bragg's peak and NBG is the number of counts for the background. Now, the standard deviation sigma is basically given by NP plus NBG to the power half, that is square root of n p plus n b g by n p minus n b g. Now, you see here that as the n p increases, the sigma, that is the standard deviation, decreases. So, counting statistics are very important. So, once we could correct all these errors or the required corrections could be obtained, then the sample's intensity, the texture intensity of the sample is basically normalized to multiples of random orientation distribution, that is MRD. So, normalization to MRD is essential in order to remove the effect of experimental error or experimental the effect of experiment or sample size or experiment size from the sample. Now, how we do it? So, as I said, after all the corrections, the pole figure intensities are obtained in terms of number of counts per second, that is CPS, per pole figure points, that is per pole figure alpha beta points. So, what we do to make the pole figure data independent of any experimental parameters, as I was saying, normalization of intensity has to be done to get a standard unit, right. So, the convention is to express that in multiples of random orientation distribution, which is known as MRD, multiples of random orientation distribution. So, the normalization factor basically n is given by, you see, integration of the intensity of corrected alpha beta times sin alpha by the integration of sin alpha, right. So, it is basically the integration over the measured and corrected intensity over the full pole figure and the weighting of the intensities with regard to their areal contribution in the pole figure. So, the intensity after normalization is equal to intensity corrected divided by this factor n. So, this normalization factor is such a factor that for the randomly oriented sample, the I normal will become equal to 1, right. For pole figures with certain texture, MRD will become greater than 1 for those positions of for which a particular HKL plane is aligned more than that of the random sample. Okay. So, finally, the conclusions. Background correction is done to measure by measuring complete pole figure away from the diffraction peak and subtracting it from the measured pole figure intensity for all alpha and beta. Defocusing error can be reduced by using a smaller divergent slit and a wider receiving slit, but it will increase the background error. The pole figure can be measured up to alpha equal to or less than 70 degrees due to large defocusing after that angle. The pole figure measures only plane normal and it does not measure even the direction, and therefore, multiple pole figures are required to measure the whole texture. Also, the reason is it can measure up to alpha equal to 70 degrees. The counting statistics and normalization to MRD is important to relieve the information of the pole figure from the experimental parameters and to represent it independently in terms of MRD in the pole figure. Thank you very much.